Hello, good evening, everyone. Thanks for joining us. We've got a session tonight on post-tension concrete. So Interspan are design and build post-tensioning contractors. We're across the world, originally Australian business, and we've come across to Europe, the UK and Ireland. We are a CARES approved PT installer, and we are a full contractor member of the Post-Tensioning Association. So post-tensioning is a technology developed in France almost 100 years ago now. Most of the initial post-tensioning that was done was in large civils, but buildings were starting to do post-tensioning sort of in the 1950s. And if we think about post-tensioning, a good way to think about it is that we're pre-compressing the concrete. So compressive stress is put into the concrete member before it begins its working life, and we position the post-tensioning system where tensions arise. So as we know as engineers, concrete is strong in compression but weak in tension. So the post-tensioning system helps us overcome those limitations.
Yeah, we've got a few images here to try and illustrate that. So you can see the box down on the bottom left. We've got a sort of simple supported beam which we're compressing. We got stress block like this here. We apply some load to it, so it's a UDL load, bend the moment. The simple supported beam, as you can see, you get a stress block in red. Up here, you've got tension in the bottom base, compression in the top. You add the decompression to that stress block. The net effect is zero tension in the bottom, or very much reduced tension in the bottom. That's what the aim of post tension is in slabs and beams and other structural members.
Okay, so where do we use post tensioning then? There's a number of places. So the one that we're going to be focusing on tonight is predominantly buildings. We'll touch on other structures in a couple of slides, but the main focus will be on buildings. So if we have a look at that, so we are looking at post-tensioning, which can span further versus traditionally reinforced, essentially. So more efficient way of spanning. We can therefore reduce the number of columns in a building. We can reduce the foundation because we've got a lighter structure. We can make it easier for internal planning, increase clear spans, thinner slabs, lighter structures, reduce cracking and deflections, so pre-compression effect. We're obviously squeezing the concrete, we're going to get less cracking. Faster cycle times, because the concrete will get up to strength quicker. It's self-supporting at a quicker stage. And there is, on taller, we can reduce the story height, or we can reduce the overall height of the building. In taller buildings, this can mean that you can introduce additional floors.
Yeah, if we're involved early enough in the sort of design process, we can influence the design where we can get most benefit out of it. The foundations, we reduce, or you can, as Sam said, reduce the story height, which you can save on cladding. Most of the time, when we reduce or convert our job, we're very late on in the process, so we usually give that extra space back to the M&E contractor, or a higher floor to ceiling height. But we're trying to get more involved in this sort of earlier stage of projects to realise the full benefits of post tension in the building.
And then, typically speaking, reducing it to reinforcement, Gary, you'd probably have half of that versus a traditional RC slab and a PT slab.
Yeah.
And then the amount of tonnage of post tensioning relative to that is relatively low.
Yeah.
So,
yeah, but the total amount of steel is much reduced. Yeah.
And then you've got less to install, smaller labour crew, and as a result of having thinner slabs, reduction in reinforcement, we also end up with the added benefit of reduced embodied carbon on a PT.
Yeah, reduced reinforcement and the reduction in volume of concrete used in a building compared to conventional RC. That's where we get the biggest embodied carbon savings, and we've got a couple of examples of that later on in the presentation. So yeah, there we go. We can use PT in all building types. If you can do an RC slab, you can do a PT slab generally. Like where we work most is in residential commercial buildings, but we've done medical, hospitals, hotels,
multi-story car parks, all sorts of things.
Yeah. That's different types of structural forms as well. Flat slabs being the most common, and sort of beam and slab options in sort of car park situations. Big transfer structures, we've got a few raft slabs, and you can do cores, but it's not so common in the Northern Hemisphere.
And just a bit of a summary of some of the predominant schemes, a couple recent, one a bit older. So Bankside Yards in London will be a 49-storey tower that's going up at the moment. Bittram Building in Cambridge is a laboratory building, and that's currently under construction. That picture was taken earlier this week. Capital Dock in Dublin is the tallest building in Dublin, residential scheme that we did a few years ago. And we've recently completed Bristol Airport multi-storey car park, which had like 50,000 square meters of post-tension beam and slab in it. A nice big job. Of course, you can use post-tensioning in bridges. Fundamental principles being fairly similar, just different shapes of structure. Couple of jobs there. We've got an incrementally launched bridge on the new structure side, which is undergoing construction in Germany. And post-tensioning can also be used as a retrofit option to upgrade older structures as well. So we've got a couple of examples of that. We've got post-tensioning tendons. You can see the ducts running through inside the box girder here to strengthen this structure. And we can also use stress bar vertically to upgrade shear strength in structures as well. Just a couple of options and applications. There are many more, but it'll be a presentation in itself. Wind towers, running tendons vertically is within the same main body of wind towers. For example, there you can see the tendons running up the inside of it and then being stressed at the underside. Containment vessels, so post-tensioning tendons run around the circumference within the wall.
Yeah, you can see the pockets of the live ends where the mouse is at the moment. Yeah.
And similarly, if you've got one that's struggling structurally, you can basically strap them up with unbonded post-tensioning on the outside. Yeah, that can be quite an effective solution for those kind of scenarios. So if we focus on the PT system that we'd normally see in our building projects, it'll give you an idea really and an overview of sort of fundamental things that you'd see. So main weight of the material is the strand. Comes on a 3-ton coil. It has to be CARES approved for us to use it in the UK and Ireland. The strands are placed within a galvanized steel duct, which we can see here. There we go, there's my mouse. Galvanized steel duct. And we have anchorages, a live end anchor here. So we've got this cast in here with the block and wedges on the end, strands running through, and then the passive anchor on a normal post-tensioned slab would be a bond length that we see here with the wires. So there's 7 wires in a post-tensioning strand, and those get pushed by hydraulic jack into this onion shape, and that forms us then a bond length and a passive anchor on the end.
Yeah. So as we stress the strands on the end of the anchor, the wedge and block system prevents the strand slipping all the way back through, and that's what transfers the compression into the concrete at the live end.
And then yeah, so in that condition, the reliance of transferring the force into the member is reliant on the anchors, but within buildings within
the
UK and Ireland
market, yeah,
we would grout them in. We'd use what we call a bonded system. So you can just about see there's a grout tube. So after the slab's cast, tendons are stressed. We'll come along later and we'll inject grout under pressure. Why does my mouse keep going? Grout under pressure through the tube that we can see here. The live end, it will flow through the duct and fill that. And then as it comes out at the end, we'll be on a catch bucket to keep an eye on how it's coming through, and then we'll lock that off. And then at that point,
once the grout's cured, the stress is locked on the full length of the tendon. So this is a little slide on the bonded system, so you can see the image there was a grout test that we done a few years ago where we set up a sample slab with the materials and materials we use to build our systems. We stressed it slightly and grouted it, and then cut sections along it to make sure that the full area inside in the duct was full of grout, which you can see there. It was a successful test. So there's other advantage of grouting it. You've got corrosion protection of the strand because it's fully encased in in concrete, you got increased, or you got flexibility for the penetrations. If you cut the strand at that point, you're only losing the stress very local to that point where you cut it, and the stress is held along the length of it. With an unbonded system, for example, if you cut the strand, you use the stress of the full length of it, because it's held on at the anchor. There's an argument that the demolition's easier, because there's less steel to cut out and cut through. You got less reliance on the mechanical anchors we said before, or the stress is along the length of it. So in an unbonded system, the anchor should be regularly checked to make sure there's no corrosion in them, because if they start to corrode, the stress will be lost along the length of it. That's why they're sort of more suited to civils structures and bridge type buildings, where structures where you're can go and access the live ends. In building situations, that's not always practical. The tendons bonded system could contribute to the shear capacity of the slab, which we occasionally use. And I said before, there's no universal effect in the strength due to any sort of local damage. And then we can utilise the tendons as part of our progressive collapse, disproportionate collapse, and robustness calculations.
There's a little animation off our website just to show you sort of the post tension in action when we do the stressing, so you can get an appreciation for the equipment being used. A hydraulic jack comes and stresses the tendons, and as they lift the drape up, we're counteracting.
Yeah, there's a load balancing of the self weight of the concrete that occurs, and when you stress the slab. So that's how we control, or we can control deflections more better than RC slab, because we're actively balancing that portion of the self weight. The portion can be up to sort of 80-90%.
And yeah, just some more pictures of a typical slab install, just to focus on a couple of the items discussed. So live end anchor, you can see that casting in the ground tube that we saw before. There's also a void former that's attached to the end, and then we've got the edge shutter here, so that when the concrete's cast, we've got a pocket to come in and do the stressing.
And it hides the wedges and block system at the end of the anchor,
which are then packed in later. Yeah.
And you can see in the picture of the anchors from above, the anti-burst steel around the anchor, as you imagine, when we're stressing the tendons, it's a lot of load focus in that area. So what the anti-burst does is confines that and stops the concrete bursting.
Yeah, in situations where we can't access the edge of the slab, we put on another type of recess. So instead of this void former here, we have what we call a pan, so that we can come in later and we can stress from the top surface of the slab. So you might have tendons running up to a core, so you need to stop them short and put this in so we can stress them. And then again, there's just another image there, the dead end anchor.
There you go, make sure that the onions are spread, and so you can spread the load again. There's this concentration of load when you stress the strands at the dead ends. And there's an anti-burst that's placed over the top of them as well.
Yeah, you can get a bit of an appreciation of the layout of everything. So we've got some edge reinforcement, so some U-bars and laces. We've got some mesh in the bottom for anti-spalling, which is something that comes out of the Eurocode. And our tendons are chaired and profiled
on plastic chairs that are bespoke made, so we can support the tendon at 1 meter centers to achieve the profile that we've designed to.
And then around the top of the column locations, there's punch and shear reinforcement, so that can either be bent links and bars, or it can be bars with shear studs or rails, proprietary rails. So that gives you a little bit of an overview, but if we actually think about how it's installed, it'll probably help everyone to sort of visualize what's going on a little bit better. So we will come in when the deck and the edge shutters have been installed. Once the edge shutter's on, we can fix those anchors along the perimeter of the slab and start pushing the strand through. Slightly different sequence of beams, so we want the bars in sequence to allow us to come in and put the strands. And top reinforcement for slab, it can only be fixed once the tendons are profiled. So usually the sequence is deck, edge shutters, we'll go around, we'll fix the anchors on, we'll push the ducts and strands through, and then the frame contractors, steel fixers will follow us around installing those U-bars that we saw, and then we'll be profiling the tendons, putting them on those chairs, and then once all that operation's complete, frame contractor can then put the punch and shear reinforcement over the top.
Yeah, it's important to understand it's just a different mindset from doing a conventional RC slab, and there's usually a bit of learning and communication and coordination with I say a new contractor or a new team who haven't done PT before in the first couple of pours, but you get into rhythm and everything sort of gets at that point, and it can be quite quick process.
So as part of our QA, we inspect the components and the installation, and then we also do a pour watch. So we'll have a guy there looking after the PT system once the concrete's poured. Obviously, things can get knocked over during that operation, so we're just there to correct anything.
Guys stomping around in a concrete boots and stamping on tendons and things like that, we make sure that we either fix it or tell them not to do it when they're running about. But yeah, it's just a different mindset to a conventional slab.
Yeah, so PT's installed, rebar's installed, concrete's poured. We've done the pour watch, everyone's happy, and then we have to think about stressing. So it's usually a two-stage sequence in PT slabs. The initial stress will happen when we get a compressive strength of 10 newtons. And what we'll do there is we'll just put a little bit of force on just to pre-compress the concrete, put a bit of force through the PT system just to prevent any early stage cracking of the slab.
Yeah, we as you saw in the picture, there's not a lot of top mesh, so they can, during the curing process, you can get some sort of plastic cracks occurring, and you want to make sure that there's a bit of compression in the slab to stop that happening. So it's a key element in our sequence, because we don't want to add sort of top mesh just to control that.
Because we want it to be efficient, because we're all trying to save carbon, materials, and make things commercially viable. So when you do the testing, it's essential that if you're doing cubes, don't cook the cubes. Take them out of the last bit of concrete that you're pouring, and put them on the deck, on the slab. If there's an area that's particularly shady,
try and
think about those kind of things.
Try and replicate what the slab's curing, rather than getting a strength from your curing huts and baths and stuff like that, because you can obviously, if it's a colder day or conditions are different to that, you won't get that comparable strength to what the slab's actually achieved at that point, which you can have. If you're not up at 10 newtons, you'll get concrete bursting, which you want to avoid.
Of course, the other thing that you can use is thermocouples. So we're seeing them quite a lot now on projects. We think we would advocate using those. Final stress then follows when the concrete gets to 25 newtons. Obviously, when that happens will be dependent on the mix. What's in there, how much replacement, grade, etc. But typically on projects,
time of year as well.
Time of year, yeah, we have to consider the mix in winter and summer. So usually on most projects that would be 3 days after the slab's cast. Might be 4 days, might be 5 days in the winter. So at that time we come on, we do the final stress, we measure the extension. The operatives measure the extension that the strand has pulled, and they feed those back into the engineers in the office to make sure that they align with the theoretical extensions from their models.
To ensure that the load that we put into the slab is the load we're expecting in our design.
Because if it's not, it's indicative of an issue.
Yeah.
Perhaps the dead ends have slipped because the concrete wasn't as strong as we thought.
Yeah, we'll find if there's any issues that, say, if a tendon's shorter, you'll get a shorter length of extension than expecting, and that could be because there has to be a change on site and things like that. So it's a good sort of QA check what we do when the extension check comes in. But once everything's okay and approved, the engineers are happy in the office, they can cut and seal the tendons at that point, where the excess strand of the ends of the anchors are then cut and the little pockets then sealed. At that point, the slab is self-supporting, so the decks and formwork can be stripped out and moved up to next. So this is where we get our advantage compared to an RC slab. So that'll be day 3, day 4, day 5. An RC slab, you'll be waiting, say, day 7 to 4, depending on geometry and concrete mix, but you're saving, if you conservatively say you save 1 day per pour, and you've got a 50-story tower, it can be a decent saving, but on average maybe saving 2 days per pour.
And here's just some images of the stressing operations. Typically, the type of things that we're stressing are these flat tendons with a monostrand jack, and this is very much the arrangement. We can see the spray marks on the strands, so those are sprayed before they're stressed, and then we can measure them there. We've got a measurement to take. Just another view there, and it gives you an appreciation for the pockets and the layout and where the grout tubes sit. So after the tendons have been stressed and the pockets cut and sealed, we can come along later when deck's removed and there's edge protection on there. We can grout up the tendons from inboard of the slab edge.
All the stressing's done inside the edge protection, which some old anchors had the grout tubes coming at the face of the edge of the concrete, which wasn't ideal once the decks were struck. And you can see in that last picture there's a multi-strand jack, which is obviously much bigger than a tail jack in the other 2 pictures. That's usually used in sort of civils or bridge structures, occasionally in buildings where you've got large transfer beams and structures that you need a lot of strands in the beam. So the issues with this is in a beam, in a building situation, is that you can see the size of it. You normally need to leave a pocket out of the slab around it so you can position it into place. You need a crane to hold it into place, so you're using the crane for probably a day, because it's fiddly to get it into position and get it on the ends of the strands, and then you've got extension checks, so you don't want to move it out and try and get it back on. So you've got a day typically out of the crane. So we try and avoid them where we can in building situations.
Yeah, we try and use the mono jack, and then all we need from the frame contractor is just a meter to be able to work in this area.
Yeah.
So grouting after within 28 days of the final stress, if because conditions don't allow that to happen, maybe it's too cold or the access isn't there to be able to go in and do the operation, we have to make sure that everything is sealed to prevent any entry of liquid, because there's any corrosion going on. And then prior to grouting, we'll air test it using an air compressor just to make sure there's no blockages.
And it sort of blows out any debris that might have got into the tendon.
And then the grout that's pumped in, that'll also displace them as well. So the grout operation will be 3 operatives. You'll have 1 on the mixer, 1 injecting, and 1 on the other end with a catch bucket. Guy on the end with the catch bucket will be looking to see what's coming through, make sure any debris come through, and we're getting clean grout coming through at the right sort of consistency. So very much a thing for an experienced operative. And then there's also checks, which we'll touch on when we talk about cares as well for the grouting operation. So
the post-tension in industry in the UK and Ireland are audited and monitored under independent body called CARES, the same company that monitor and regulate the rebar industry. So they've set out a set of rules that we all have to follow from the model spec, which we are audited against that, and the 9001 ISO 9001 system that we have that make sure we comply with what CARES require. So there's 2 key components that the system must be certified by CARES, and that's the strand and the grout, the 2 probably most important elements. So they are independently audited, and we can only buy from CARES approved suppliers. And then they've got rules for the anchors and ducting and how we do certain elements. Also, when we're grouting, there's a set of tests that we need to carry out to make sure that we are complying with the fluidity, the amount of bleed that you get. You don't want too much, and the strength, all that sort of stuff. So there's a suite of tests that our guys carry out on site to make sure that it's all within spec.
Yeah, there's a bit of a change undergoing with the model spec at the moment. There's a revision going through which hasn't been released yet, so we're just part of the working group on that. There's going to be additional requirements for the anchors and some changes to the
frequency of the grout tests, because some of them are quite onerous, so I think that they're making them less frequent.
And then just an example of what we do as a business as well. We've got a very robust set of forms that we do for each of the operations. And yeah, we ensure that everything is filled out and correct.
But this will be similar for all sort of UK and Ireland based contractors who are complying with CARES. Just done slightly different way or the same way, just keep the quality across the industry at a good level.
And that goes into the O&M manual at the end of the job.
Yeah.
Of course, you know, things can and do go wrong due to various factors. The main ones we'll talk about over the next couple of slides would be concrete blowout. So the tendons bursting out of the concrete, and that can be down to a number of reasons. The grouting is essential. We need to make sure that's done with the right material, as we've said with the CARES, and we're doing the right tests, and we've got the right people doing installation and grouting. Cutting of tendons. So if someone comes in to make an opening, they might want to put some services through the slab. They don't realise it's post tension, they core through the slab. That can be an issue. Issues with cracking due to various reasons, which we'll cover, and punch and shear failure due to incorrect design and detailing. So a few pictures of blowout, they look pretty horrendous, and yeah, they can be a bit of a nightmare to fix, but they can be fixed. And that's usually down to a number of factors. So it could be the quality of the concrete, bad compaction. So, you know, sometimes these areas can be quite congested. You've got an anchor, you've got the anti-burst reinforcement, you've got the reinforcement around the edge of the slab. You might have
casting fixings for cladding and things like that. We've got to coordinate. So it's one thing we were speaking to the frame contractor or concrete guys that we vibrate around the anchors as a key part of their concreting process.
Yeah, and then I think factors like the concrete strength. So yeah, if you cook the cubes because you think you'd be able to move a bit faster, you're actually just cheating yourself. So it's always best to match the conditions. And there might be errors in installation as well. So if the anchor's set too high, there's obviously not much concrete above it, that can cause it to come out as well. So the implications are, massive health and safety risk during the operation if it suddenly fails. And also, the knock-on effect of them remediating that. So you need to detension the PT system, and then the concrete repair needs to happen. And no one wants that on their program, do they?
No, the reason we're highlighting this is because we've learned from these situations and avoiding them more and more, which is it's good for us to be aware that things can go wrong rather than just be sorted all the time.
Grouting, with a CARES approval, and we use pre-bagged proprietary grades and doing the correct testing to be compliant with CARES and our own QA. And it's essential that it's done properly. There's no voids within there because we don't want to see corrosion later on.
Yeah, we've been called out to a few older jobs that are done, say 20-25 years ago, where the grouting was late, or there was no sort of CARES approval at that point, so the quality was not as good. So we've seen some issues with poorly grouted tendons that have corroded over those years, which we're going to start repairing. So it emphasises the key quality systems that we've brought in.
And then cracking, usually in a post-tension slab, the main reason the cracking would be issues arising from restraint, and we just need to be conscious of, layouts of the stiff elements going up building. Make sure that we're detailing temporary release around there, so that can be either by these proprietary temporary movement joint lockable dowels, so they allow the movement in the early stage, and then they're locked in later, or strips.
Yeah, the restraints cause us, as we had concrete, obviously all shrinks and moves, but as we stress the concrete, we're enhancing that movement because we're compressing the concrete. If you get too hard elements, concrete wants to compress towards its sort of stiff elements or the centre of gravity, and it's stopped from doing that, and that's where you can get restraint cracks. So, as Sam said, temporary release joints allow us to avoid that problem, and that's something that the early design stages and pre-construction that we make sure that our clients understand that these are needed in certain places because it can affect their program and method construction.
And this is an example here where we've visited the slab, and yeah, we can see there's some restraint cracks at the corner of the slab because they've got beams running either way, and then the result of that being neglected and left was that there was a little bit of corrosion locally to the post tension system.
Yeah, that's on an external car park, so there's been some moisture running through that crack over the last 25 years that caused the tendon to corrode, expand, and sort of spoil the concrete. And back in the early 2000s, there was no bottom mesh needed. So if there was a bottom mesh of steel here, that would have helped contain the cracks a little bit better. But there was only post tension in those slabs back then.
And yeah, cracking due to probably down to thermal shrinkage. So just basically, we haven't got much reinforcement in the top of the slabs that we touched on. So you need to make sure that you're carrying out the stressing procedures in line with the spec, 10 newtons for initial stress, 25 for the full stress.
Yeah.
Otherwise, yeah, you're going to be facing remediation to those cracks, grouting schemes, resin injection, that type of thing. Punch and shear failure, particularly where we're driving down the thickness of slabs, and you've got small columns. We can get down to 200 thick in a residential slab. That's on a small column. Obviously, punch and shear detailing is absolutely crucial.
Yeah, we'll go into that in a bit of design of how we look at that, how crucial it is when we're pricing a job and when we're designing a job.
Drilling and cutting into bonded PT slabs, there's some clear guidance through the Post Tension Association, which is available to download, which gives some clear guidance on how to approach making openings.
So yeah, there's a bit of a myth busting exercise that the PT wanted to do, because every time we go to meetings, and it's, we can't cut through PT slabs, it's not flexible, and it's a misconception from the old unbonded days. It's a bonded system, it is flexible, you can cut it, you can modify it. You can't just cut huge holes in an RC slab without any ramifications from a structural point of view. You've got to strengthen it or support it. It's the same with PT slab. It's just you've got an extra layer of, you probably need your either PT contractor who carried out the work or another PT designer or contractor to review the post tension design if the structural engineer is not experienced in that, because post tension slabs are designed for the bending moments that we're expecting, and if we cut a huge hole in one big bay, bending moments will change in the end bays or the promoted bays or whatever, and we can advise that it's all good what we've got, or we'll need to put some further strength in the works or supports in there. It's just an extra step of your PT contractor or consultant will be able to do that if you don't have the in-house ability in your own structural consultancy.
Yeah, so yeah, top tip, download the guidance and consult the PT to design. In terms of what we usually see, shallow fixings on the soffit, cable trays, etc. You can put those anywhere because you've got the cover to the underside of the tendons. You're not going to encroach on that. For deeper fixings and for small holes, do a bit of a pilot hole. Use a masonry drill bit if you're trying to locate the tendons, rather than using diamond coring straight away. And then if you hit the tendon, you can see that, and you can just move across to the side and then continue. Yeah. But also spacing between the tendons, typically speaking, tendons would be 1.2, 1.4 meter centers in a building. So you've got plenty of
there's lots of
scope
flexibility
for holes in between that for the small ones. Of course, yeah, as Gary was saying, larger ones can be accommodated, but we just need to do the check-in, and there may be some strengthening required depending on size and location of those opening. So there's some quite interesting stuff on it, investigating older PT structures in here. So there's a few ways and means of identifying post-tension slabs and buildings and civil engineering structures that are post-tensioned. Obviously, we have as-built, but depending on the conditions on site, you might want to do further investigation to get a good understanding of what's in there.
It's a really relevant subject these days, where reuse and repurposing of buildings is is where everybody wants to start when they're looking at a building project rather than demolition. So yeah, there's as Sam said, various different ways of looking at it. The as-built drawings is the first place to start, but there's a few jobs that we've been involved in and they don't exist, unfortunately. So you can go visually inspect the slab to see where you think tendons are. There's a few markers. You can sometimes see the chairs, or sometimes they've been marked out before. And if you don't have that luxury, you can start drilling into the slab to try and find them if you want. But there's also another part to that of using these GPR scanners to scan the slabs and pick up the tendons and rebar that's in there. And there's a picture of me and Sam up at Edinburgh Airport scanning the slab to see the tendons. So we done a bit of a test there where we were drilling the slabs to find the tendons, and then we used the GPR scanner to verify what we found. So it was an interesting example of doing that there.
But what you can do with this is, perhaps if access is limited, you don't want to be taking possession of the area of the building or structure. You can come in and do the scanning. It will give you an idea of what's going on ahead of coming in and doing the intrusive. So it just helps you sort of de-risk things a little bit.
Yeah, and identify areas where it might not be as what you expected as per the drawings, or areas where the tendons might not be present, or whatever. You find voids in the slab, which suggests an ungrouted tendon. So it allows you to focus your sort of intrusive investigations.
There are a couple of different things going on with the different kit and how they work here, because just to try and keep things as clear as possible, we've got the location using the GPR technology. Things that are close to the surface will be highlighted in red as they get closer. But where we look at ultrasonic velocity pulse type equipment, when we've scanned, we've located, and then we come in and use this technology to see if there's any voids. The way that this works, the voids will be represented as red. So red is bad here, but not necessarily in the GPR scan, just to clear that one up. And then, as we get down to intrusive investigation, so it might be small holes that we drill and then just localized opening of the ducts. We can also do much larger ones where we want to come and make modifications and investigate what's going on. See here, there's an older structure here that's been ungrouted for some time. And that can be used across buildings, civil structures, same sort of technology. So design, Gary, this is your bag.
Yeah, so we'll do it quickly. So the design of the PT elements are set out in Eurocode 2, and we use the Company Society's TR43 as its sort of base guidance in the UK and Ireland. And we'll design very similar to the way that you design a conventional RC slab. We typically will use 3D FE software to analyze and design the PT slabs. So we'll model that slab with the correct geometry and appropriate stiffness for columns and cores. Make sure that we're modeling the structure properly and getting the correct sort of analysis results. And we'll put the load to the slab that the structural engineer gives us, or the contractor says this is what's going to be applied to the slab, and we'll do that in load combinations as set out in the code. We will set up a load history deflections, which is a system within RAM Concept, which is the program we use, which models the slab for its lifetime, and we can apply loads that when they're applied, and the concrete will age and the E value will change over time as it's expected in real life. And obviously we'll design the slab for serviceability, make sure deflections are all okay. We'll do it for the ultimate limit state, obviously strength. We'll check punching shear, which is key items as we've spoke before, where we're reducing slab thicknesses. It can be the element that defines the slab thickness rather than the span. So the span might work easily, but the columns are small and the slabs are thin, or we want them thin. It might define the 225 to 200 slab, depending on what punching shear shows. And then obviously we've got to make sure there's a minimum level of P&A and pre-stress in the slab. So TR43 sits out, it can go from 0.7, which is the lowest, and up to 0.3 is average for flat slabs. we normally design between 1.1 and 1.4. It seems to be the sweet spot for our designs. And then we'll do Interspan and we'll do all this sort of wee bit detailed. In the slabs, we'll set up sort of time enforcement, disproportionate collapses, Eurocode 2, and whatever building category and class that you're working to. And yeah, we're applying a lot in load combinations, said before, and we'll profile attendance that match the design model on our drawings, and then we'll get their extensions from the model of what we expected the strand to extend, and check that. That's what's used to check against what the guys measure on site.
Okay, and this touches on a bit more of what we saw with the restraint cracking.
Yeah. So as we spoke about we've shown this the example below. So you've got the top line of the sort of the GA drawings. You've got a favourable one, so all your stiff elements are. You've got the one in the centre of the core, and you've got sort of the stiff elements in one direction rather than in two directions. If you look at the bottom below, where you've got stiff elements against each other in two directions, it's going to stop the slab wanting to shrink and move. So what we do is we'll use the lockable dowel or a post strip or some sort of detail to allow the slab to shrink separately. That's something we just got to be conscious of from the start of the design to make sure it's incorporated from the beginning.
Yeah, so from a construction point of view, if we're looking at this floor plate, you might use that temporary movement joint to make your stop end if the contractor wanted to do two pours.
Yeah.
So that forms your construction joint, but also does all that early stage movement. If you were to do it in a single core, you just put the temporary movement joint or pour strip around the core.
Yeah. And then one question we get asked often when we're looking at design is, I've got lots of things I need to put into the edge of the slab, can you coordinate? The answer is always yes. We've built and designed lots and lots of buildings, as all sort of PT contractors and designers have, and we can coordinate around anything as long as we know it's there at that point. When we're doing our design, if it's there, we put it in our drawings and we'll coordinate around it. Our live ends are relatively flexible, probably more flexible than the cladding and fixing points for balconies and things are. So we always like to go second. If you give us what you've got around your slab edge, we'll coordinate attendance.
Yeah, there's a good little example actually here, because you can see that where we've got this sort of triangular shape that represents a live end on the drawing. All these little numbers are the profiles of the tendons. So you can see here we've got two tendons. They're matching tendons because they're joined by this link. We've got a live end on this side, but we weren't able to put the live end on this side, so we just flipped it around to the live end somewhere down here, and we've got the dead end which stops short of the slab edge. And then we've got another example here where we've got a tendon that we've just slightly deviated just to avoid a clash on the edge of the slab here.
Yeah. And it's just some pictures of outputs from the RAM model. So we'll model one slab at a time. Generally, you approach a PT slab. So you can see in that top image there, we've got all the tendons modelled. They're profiled with to mimic the bend moment. So you'll get tendons at the bottom of the slab where you're expecting tension. So in the centre of the slab, and then at the top of the slab over the columns for the hogging moment, so you can see the profiles in that 3D image. And then the picture below is of the deflection plot, so be very familiar to most people, where you've got red showing where it's deflecting more, not necessarily failing as some people think, but it's just the scale of it. So that maybe be up to some 20 or 25 millimeters on this long-term deflection plot. But yeah, we'll present this as part of our calculation report to the structural engineer for their review and consideration as part of the full building design. And this is some typical drawings of our reinforcement detailing. This is the Battersea power station, I think it is, where we've got a typical flat slab, residential slab, but it had lots of elements going to it. There's a sort of transfer beam towards the top. There was big outrigger walls that needed the slab to act as a flange, so we were detailing all that in our drawings as part of our PT slab design in coordination with the structural engineer. What we've got to always remember is we are designing this slab to the structural engineer's performance spec to make sure that the slabs comply with the overall building design. and it's an example of punch and shear detail. It's a quite a good image and drawn from a job we'd finished in Luton at Barnfield College, where.
So it's this slab here from this model.
Yeah, and the crane operator took that photo, and you can sort of compare it against the drawing. It gives you an idea of what it looks like, and you can see the punch and shear heads over each of the four internal columns, and there was none around the edges because there's a pretty significant drop beam that was on this job.
So if you're curious about how to, I've got a job, I'm considering my options as to which way I'm going with the structure. How do I get a PT option? Well, the best thing to do would be to send it across, and we can have a high level look at it. We don't need a lot of information.
So also your friendly post-tension contractor from the PTA.
Yeah. So yeah, don't need a lot really, just some early stage drawings, what the building is, what the use is.
Yeah, I think
any loading if you've got it.
What the sort of PT industry is just looking for is just give us a chance to give you an option in stage 2, for example. Got a building, we'll give you very high level rates. So consider it. Here's what the slab we think the slab thickness is be. Here's what we think columns can be. Here's what the rebar we think the rebar content will be for a PT slab, and give you an indicative price for the post tensioning to pass on to the PQS. So it's just part of the conversation. If it happens, it happens. If it doesn't, you've had a shot at it. And it's just trying to grow the awareness of post tension and buildings and other elements, and
help the market get a bit of a feel for it, because what we don't want to do is that it gets someone tries to interpret the costing and gets it wrong. So it's a big thing.
And at this point we can advise on the embodied carbon of that design.
You can do a quick run. So there's we predominantly would use the iStruct's carbon calculation tool, which is readily available, and we'll input the RC scheme versus our PT scheme, and get some comparisons and send them across.
This project here was a job for one of our clients where they were embodied carbon. It was a job up in Cambridge, so I think it was for the university. So the embodied carbon was key, and it was driving decision on a lot of the design items that they were looking at. So we gave this option to our clients, so you can reduce the slab thicknesses down. We took 25 mil off each of the slabs, and gave them the sort of carbon savings. So there's a decent reduction, volume reduction in concrete, which drove the sort of saving in embodied carbon. But what we did on this one is we didn't just use the same concrete mix. We used, the RC had a higher GGBS mix than the PT one, because you generally have a lower one for PT, and we were still in front, mainly driven by the reduction in volume of concrete.
That gives you an overview of that. There's some published data out there as well for load span tables and versus carbon as well.
Yeah, so we've knocked this together based on some data from the Concrete Centre, where they've got densities for rebar and PT against a sort of conventional option, and we converted that back to carbon emissions, and you can see the PT, for example, look at 8x8 meter span and residential loads. Your PT's got a thinner slab compared to your RC option at 250, so we've got lower embodied carbon per meter squared. So we've got 84 to 98. But that's just a very typical example of a reduction in embodied carbon for a PT slab against an RC flat slab.
So in terms of real life experience and projects, recent ones, there was one that we did up in Salford. The engineer's scheme was RC slabs of 275 thick with a reinforcement density of 160 kgs a cube. So we had a look at it. We managed to get it down to 220 millimeter thick PT slabs. A significant reduction in concrete and reinforcement, which then meant that we unlocked over 1,300 tons of embodied carbon saving on that particular scheme. So That one's currently under construction.
Yeah, almost finished now. Yeah.
One that's completed. Job in Cambridge Park Street used to be a multi-storey car park, and there was a scheme to build a Stay City hotel with retail units, and then we got 3 levels of underground parking, I believe. And so what happened with this one is looked at the upper levels, suspended slabs, got the thickness of those down, and then as a result of the weight reduction, we were actually able to re-engineer the foundations because the structure was lighter. The advantage there being program saving, material saving, and carbon saving as well.
Yeah, I think that the program was the big key, and reducing the amount of piling was key for the client on that job.
So 930 tons reduction in the body carbon just for the material saving. So it's significant. So that brings us to the end. It's a bit of a whistle-stop tour. There's a lot to cover there. Some of the items in there would probably deserve a session on their own, but hopefully, that was informative.